Objective 2, new functions from old functions. This is section 1.3. Combinations of functions. Two functions f and g can be combined to form new functions. The sum function, the difference function, the product function, the quotient function, in a manner similar to the way we add, subtract, multiply, and divide real numbers. So we do those things with functions, and so it's interesting that it's not just with numbers that we do those things. The sum and difference functions are defined exactly the way that you would think. If you want to define a sum function given two functions f and g, what you do is you add f of x and g of x. Similarly with subtraction. If the domain of f is A and the domain of g is B, then the domain of f plus g is the intersection A intersect B, because both f of x and g of x have to be defined. Okay, so remember your intersection of two sets. Okay, this is the set of all elements of both A and B. So a thing has to be in A and it and it has to be in set B, both. And if it's in both, then it's in the intersection. For example, you have your square rooting function, f of x equals square root of x, and that has a domain, and that is the set of non-negative real numbers, the closed interval 0 to infinity. And the domain of g of x is set B, which is the closed interval negative infinity to 2. That's the set of x values that are allowed for g of x. Now, if you're going to have the sum function f plus g, which is f of x plus g of x, which is square root of x plus the square root of 2 minus x, and you have to get the domain of this new function, the sum function. It's the intersection of the two domains, the set of all numbers that are in both sets, and that is only the set of numbers between 0 and 2 inclusive, the closed interval 0 to 2. Similarly, the product and quotient functions are defined the way you would expect. Fg of x is defined to be f of x plus g of x. And similarly with the quotient function. The domain of fg, it's the same thing. You do the same thing. You take the intersection of the two sets. But it's different for the quotient function. We can't divide by 0, and so the domain of the quotient function, f over g, f divided by g, is the set of all x that are elements, the set of all real numbers x, or the set of all elements of the intersection a and b, such that, and there's an extra thing, g of x is not equal to 0. Okay, so it's things that would be in the intersection, the way you would compute it just for the sum, difference, or product functions. But then there's that extra thing, any x value that makes g of x 0, that can't be included either. That has to get thrown out of the domain of f over g. We could write it this way, okay? We could say we could call it an intersection of three sets. Okay, we could say domain of A domain of A intersect the domain of B which is A and B, intersect this other intersect everything that doesn't make g of x 0. All the x values that make g of x 0, the ones that do have to get thrown out of the domain, so we could write it as an intersection with that third set. And so, anything not in all three of the sets gets thrown out of the domain of the quotient function. So, set of all x such that g of x, you got to be okay with this set too. G of x can't be 0 because it's a denominator and you can't divide by 0. So that's another way to think of it if you're comfortable with the set theoretical notation. For instance, if f of x equals x squared and g of x equals x minus 1, okay, now if you think about the intersection of the two domains, well, you're not throwing out anything for those two sets, the domain of f and the domain of g, because the domain for each of those things is a set of all real numbers. But g can be 0 if x equals 1, so we're going to throw that out. So any x value has to be good with all three of those sets. The domain of the rational function f over g of x, which is x squared over the quantity x minus 1, is set of all x such that x is not equal to 1. In interval notation, it's a union of two open intervals, negative infinity to 1 and 1 to infinity, right? This entire thing, that doesn't include 1, correct? 1 is not in either one of those things in the union of the two sets. So now we've talked about intersection. Now let's think about union for a moment. Intersection was the set of all things that are in the one set and in the other set. You got to be in both to be in the intersection. But the union is a set of all things that are in either the one set or the other set, or both. So we associate the word or with the union of two sets and the word and with the intersection of two sets. There's another way of combining two functions to obtain a new function. We talked about adding them, subtracting them, all these other things, but there's a whole other way that actually we don't really do with numbers. Suppose that y equals f of u, and it's the square rooting function, the square root of u. Okay, so y is a square rooting function, and for convenience sake, we're letting the variable be u. But then u itself is a function of x. U equals g of x equals x squared plus 1. Since y is a function of u and u is a function of x, y is a function of x. And so we can compute this by substitution. Okay, y equals f of u, but what is u? Okay, what is u? U is the same thing as g of x, and so g of x can be substituted for u, and we indeed do that. We put x squared plus 1 in there for u, meaning since we're running that through f, we're going to be taking the square root of that x squared plus 1. The procedure is called composition because the new function is composed of the two given functions f and g. Composition of functions. In general, given any two functions f and g, we start with a number x in the domain of g, okay, and find its image, g of x, right? What's the output? What's the image? So you got to start with g, the inside function, because if x is not in the domain of g, then that particular value of x is a non-starter. Now, this g of x is going to turn around and be an input for another function f. If this number g of x is in the domain of f, then we can calculate the value of f composed with g of x, or we could just say f of g of x. The result is a new function, which we could call h of x if we like throwing in lots of letters. F composed with g of x obtained by substituting g into f. It is called the composition or composite of f and g, and is denoted by f little circle g. But when we see that little circle, we just say composed with. F composed with g. So a definition. Given two functions f and g, the composite function f composed with g, also called the composition of f and g, is defined by f little circle g of x, so that's just one function there, and it's defined to be f of g of x. So that the input for f is not a number, we're used to that more, but it's another function that's the input of f. Definition of the domain of a composition. The definition of the domain of the composition. The domain of f composed with g is the set of all x in the domain of g, such that g of x is in the domain of f. So it's kind of a two-step process here. X has to be in the domain of g, right, because this is f of g of x. And what if x were not in the domain of g? Then we couldn't even think about, running the value through g and running the result through f. That particular value of x would be a non-starter. But then once you do that, the output, g of x, that's got to be in the domain of f. So it has to clear two hurdles. So it's this is a definition that you should memorize for the domain of a composition. The domain of f composed with g is the set of all x in the domain of g, such that g of x is in the domain of f. In other words, and this is helpful also, f composed with g of x is defined whenever both g of x and f of g of x are defined. Okay. Notice it doesn't say whenever f of x is defined. Okay, that's not there. It's not necessary that you need to be able to run x through the function f and get something. Okay, it's only g of x and the composition. And here's a figure to show, in terms of the old function machine, this is an adaptation of the old function machine, the idea. You got an x, you run it through the g machine, you run the result through the f machine, and you have f of g of x, and that's what the composition f composed with g really means. Okay, it's two machines for the composition. Okay, we learned about the machine when we were learning about functions in general. There could only be one output if the thing is going to be a function machine and not just a relation machine. But now you got two machines, kind of extending the idea. Example, if f of x equals x squared and g of x equals x minus 3, find the composite functions f composed with g and g composed with f. Okay, so the composition could go either way. You think they'll be the same? F composed with G and G composed with F, you think they'll be the same? Well, let's see. Okay. F composed with G, now we know that is F of G of X. Okay, now what is that? Well, F of anything is the square of that thing. Right? So all I've done here is rewrite this equation here using parentheses instead of the symbol X. And so F of anything is the square of that thing, but now what's the thing going to be? The thing is going to be G. The thing is going to be G. And G is X minus 3. That's the input. Okay. Now we might, be content to leave it like this. Or we might want to, write it out as something in the form ax squared plus bx plus c. We could FOIL or use a special pattern, a squared minus 2ab plus b squared, to get x squared minus 6x plus 9. And that would be the answer, right? That would be, what's the composition of the two functions? And so we made a new function from the two, and it's a quadratic function, x squared minus 6x plus 9. Okay. Now, G composed with F, what is that? We might think that that should be the same thing. Maybe we doubt it. Okay, so G of f of x, G composed with F, of course, is G of f of x. So now F is the inside function and G is the outside function. Well, G of anything, what is G of anything? Well, G of anything is that thing minus 3. But now what is the thing? The thing is F. And what is F? F is x squared. And so G composed with F of x, or G little circle x, is x squared minus 3. Remember, the notation
they are different,
F little
right?
circle G,
G composed
means
with
the function G is
and
applied first, and then
F composed
F is
with
applied
G,
second.
they are different.
So
It's
kind of like
you
a
can
right
switch
to
them that
left
way
and change the result. A right to left. A function can also be composed with itself. We could have talked about F composed with
In
F,
example 6,
or G composed
F
with
composed
G.
with
G is the function that first subtracts 3 and then squares. G composed with F is the function that first squares and then subtracts 3. Interesting. It is possible to take the composition of 3 or more functions. For example, the composite function f composed with g composed with h is found first by applying h, then g, and then f, right to left, as follows. Okay, so f composed with g composed with h is f of g of h of x. Okay. Okay.